Okay, so in this video, we're actually going to be putting together a Laplacian mechanism, a Laplacian randomized mechanism, which we're going to use to perform two different kinds of queries, sum and mean. And we're going to see that the way in which we choose our betas, the ways in which we formulate the amount of Laplacian noise to create is adjusted based on the sensitivity of sum and mean, such that for mean, which has a smaller sensitivity, we end up adding a smaller amount of noise. So let's jump in. First, we're going to say our epsilon, so our epsilon budget for our single query is going to be 0.5. And now we're going to import numpy as an np. And let's create a database, which we're going to query. And as you will remember, all these databases, they're ones and zeros, right? And so this is how we know that the sensitivity of addition is only 1, right? So because if I were to say, so the sum is 54, right? But the maximum amount that this could change if I removed any one of these entries would be 1, right? But if this database were, say, a database of 2s, 0 to 2, well, then the sensitivity would actually double to 2, right? Because the maximum amount of the output would change if I removed the entry could be as high as 2, right? So, but in particular, because we know this sort of a priori knowledge about our database, it's all zeros and ones, just counting the sort of specific entries in the database, then we can know that our sensitivity for a sum is simply 1. So let's jump into our first query, which is simply the sum over the database. So now let's create our mechanism. So we'll say sum query. Mechanism m. So this is a randomized mechanism. So we'll say Laplacian mechanism. We have a database and we have our query. So our Laplacian mechanism, actually let's go ahead and put in sensitivity of a query. So now the first thing we want to do is we want to calculate what the beta should be for our Laplacian noise. So we're going to say beta equals sensitivity divided by epsilon. So as you might remember, this is how we calculate the correct beta for Laplacian noise. And then we're going to say the amount of noise is equal to, we gotta convert it to, let's see, what type was this? Okay, torch.tensor. So we're sampling values from 0 to 1, and according to this beta spread parameter, this query is actually this function. So query database plus noise, and this is our Laplacian mechanism. So let's use it. Let's try it out. So Laplacian mechanism, database, sum query, and sensitivity of 1. Boom. As you can see, every time we query it, it's a little bit different. The true answer is 54. So as you can see, when we run this, it's sort of just above and below 54. Pretty cool. And I think I might have said that this was between 0 and 1. So Laplacian, it's not a range between 0 and 1. It's this is actually a mean centered at 0, and then beta is controlling the amount of spread. Okay, so now let's do this for a mean query. So def mean query db equals db sum. Actually, we could just do torch.mean. Awesome. And we have 100 entries in our data set. So the thing here is we know that the sensitivity is actually going to be 1 divided by 100, right? Because it's the max amount any entry could change divided by the total number of entries, because that's sort of, the output of any query is being divided by that. So the sensitivity is much smaller for mean. So if we were to use our Laplacian mechanism on the mean query, it's 1 divided by 100. And so now, as you can see, the noise is much smaller. The noise is, just, it's 100th smaller, right? It's quite a bit smaller. Whereas if, see this one bounces around by multiple values, 54, 53, 57, 51, right? So the noise is actually quite larger, whereas the noise here is much smaller, which is also appropriate because the output is also quite smaller, right? And now the next thing to also remember is that this epsilon is measuring the epsilon that we are spending per query, right? So if let's say we had a whole budget that was an epsilon of, say, 5, then we would need to sort of partition this. We could do 10 queries, each with epsilon constrained at 0.5. And so now let's try something else. So now if I say, let's say epsilon equals 0.00001, a very, very, very small epsilon, so almost no leakage. Watch what happens to this. So previously this was dancing around, kind of the 54 range. But now it's all over the place, right? You see how much random noise is out of this? And this is because, we're not leaking hardly any information, because basically we're just returning a really big Laplacian distribution, right? And same for this Laplacian mechanism, right? So as we tune our epsilon, as we make our epsilon lower, we're actually increasing the amount of noise that we have to add in order to be able to get a certain, to get this really constraining level of privacy protection. And so the other interesting thing to remember is that this is the same exact relationship that we saw when we were working with local differential privacy in the context of coin flipping, right? So the more noise that we added, the more protection, the more plausible deniability that we gave each participant in our survey, the more randomized our results were looking, the more randomized our analysis ended up being, and the more individuals we needed to actually work over in order to be able to get accurate statistics, right? And so similarly here, if we have mechanisms, functions on our data set that have smaller sensitivity, we can actually add less noise overall, simply because we're asking for a function that's just less sensitive, right? This function doesn't naturally try to leak as much information, right? So we still have this really close relationship between sort of sensitivity, privacy leakage, and the number of entries in our database, and the accuracy of the output result, right? And so there's kind of a trade-off between these 4 different things, and it's really important to understand how this trade-off works when you're actually using these mechanisms in the real world. So I hope you've enjoyed working with this project, and in the next section we're going to jump into some more different kinds of mechanisms and ways you can use differential privacy.